I am pretty certain that I have added this page to your packet, the product of the sum and the difference of two terms. And so we're going to practice some things with multiplication so that we recognize this pattern, and then it will make it much more obvious to us how to factor these. So you're going to notice we're going to have the same two terms, but in one set of parentheses it will be a plus in the middle, and in the other it will be a minus. So you might recognize a pattern, I hope, before we get too far down the page. You recognize the pattern, but initially I'm just going to show you that you already know how to do this, and if you just simply distribute, you will come out to the same thing. But then we're going to talk about the pattern because it's much more expedient to use the pattern. This is also something I pointed out to you when we were multiplying, but we did not have that many problems that fit this pattern, so we didn't worry too much about it. So a times a squared, a times negative ab, remember we're going to write them in alphabetical order, and then b times a, also ab, but now positive, and then b times negative b squared, and then when we simplify, the two terms in the middle make a zero pair, and they would be gone, and we would just have a squared minus b squared. So that one had two different variables. Let's try number 2. X times x squared, then my outside, x times negative 6x, then now it's 6's turn, 6 times x, positive 6x, 6 times negative 6, negative 36, and once again I see that the two middle parts would cancel each other out because they add up to 0. So I just end up with the first term squared and the last term squared. So you can continue doing it the long way, but I wouldn't suggest that. Instead, if you see that in the two binomials things are the same except one is a plus and one is a minus between the two terms, then you know the middle will cancel out and you can just square the first term. So x times x squared, and square the second term. 3 times 3 is 9, and put a minus in the middle. It will always be a minus in the middle because the signs are different, so it would be negative. It can work when we have numbers in both places. 5d, remember 5d squared, because it is 5d times 5d, makes 25d squared. And g times g squared, and once again minus in the middle. The two middle portions, if we did it the long way, would just cancel out. So go ahead and pause me, and then I'm going to work the rest. You can come back and check to see if you got indeed the same answers. And then I'm going to want you to work the right-hand column on your own. Okay, now if you see number 5, did you try it first? If not, pause me so you can try it first and have a good way to check and see if you're on the same page. Alright, so you're back, and I hope that you, as you're comparing your answers, that we got the same answers. Notice number 7 looks a little awkward with the constant at the beginning, but because we try to avoid having a negative as the first term, we would just leave that as 25 minus 9x squared instead of negative 9x squared plus 25. We would leave the minus in the middle. We do need to keep them in the same order, so 5 times 5, that's that we often express this pattern as a plus b times a minus b is equal to a squared minus b squared, which is actually problem number 1. So if I see those two binomials, and I see that they are the same except the sign, so it is the sum and the difference of the same two terms, then there will be no middle term. It will just be the first term subtract the first term squared, subtract the second term squared. And I say squared because we're doing the same thing times itself. 2x times 2x, 8x times 8x, 3 times 3. The last one is always minus. If it was not minus, then there would be middle. Okay. All right, so I will want you to finish the other side. Column B, it's just more of the same. But then we're going to go on to go in the other direction because this unit is about factoring. All right, so on the other side of the page, and maybe you have a copy that this is a little more readable, but this says factoring the difference of two squares. And so now what we're going to begin with is going to be the difference of two squares. So difference, it has to be subtraction. Otherwise it's not difference. They both have to be perfect squares to use this pattern. So if they are not both perfect squares, like we can't break them up into the exact same number 3 times 3, right? Then we can't use this pattern. All right, so this is just going in reverse of what we just did, and basically we're finding the square root of each term. One set of parentheses is going to get a plus, one set is going to get a minus. Square root, if you don't know, for instance, if I had x squared subtract 256, and I don't know what number times itself is 256, and it's too big for your factor sheet, then on your classroom calculator, if you use second and then x squared, those are the keystrokes to get the square root. When the square root pops up, then you would type in 256 and hit equal, and you'll find that the square root of 256 is 16. So we would have x plus 16 in one set of parentheses and x minus 16 in the other. By the way, it does not matter if you want to write the plus in the first set or in the second set, but one needs to be positive, one needs to be negative. The two factors, that's the two sets of parentheses, will look the same except the sign. All right, so we have some smaller numbers to practice with, but I wanted to be sure to let you know how to find the square root if you did not know the square root of the number. If you're doing square root and it comes out to be a decimal, then that's not a perfect square, and this pattern does not work for that, or we may need to find a GCF first. So as we work down column A, there are two terms. It is a minus in the middle. They are both squares, two sets of parentheses. X squared means we're going to put an x in each set of parentheses. Y squared means I'm going to put a y at the back because it was the second term. One gets a plus, one gets a minus. That's it. And you may fill in things in different order, but that's how it's going to end up. So it's like I'm thinking about this first term as being, so this one, to get x squared, I would need an x in both of these. And to get the 100, square root of 100 is 10, not 50, doesn't mean half, square root. One would be a plus, want a minus because I need a negative 100. So this one looks a little awkward because we've got the 25 first, but keep that one first. So 5 times 5 is 25. And then to get a squared, a and a, one's a plus, one's a minus. So we're basically, to find the numbers that we're using, we're doing square root. So the square root of 225 might be a good one. You might use your calculator. It is 15. So I know both parentheses for the first term in each one is going to be 15, and then plus x and minus x. You might have to find square root twice. Like they may not just be just an x squared. So 4x squared would be 2x and 2x. 49, 7 and 7, 1 plus, 1 minus. Remember that these answers will look like your multiplication problems did in the earlier lesson, the first part, the other side of this page. 5a plus 4, 5a minus 4. Square root of 100, 10, so I've got 10x, 10x, 3, 3, 1 plus, 1 minus. Maybe I'm just a positive person. I tend to put my pluses first. Nothing at all magical about that as long as the signs are different. Number 8, the way this workbook was set up, they may have just intended that you would just, those are both perfect squares. But technically, we should be in the habit of finding a GCF first. And in this case, there is a GCF. 4 goes into both of these. So 4 goes in, and then I have 36x squared minus 25. And then that is still perfect squares in here. So the 4 that's on the outside stays outside only one time. And then 6x, and then 25 is 5 and 5. And I'll mix it up this time. I'll put my minus first. So at this point in your factoring experience, you might have written 12x plus 10, 12x minus 10, but we really don't want anything in common in that parenthesis, so we should try to be in the habit of always taking out a GCF first. So that page is kind of to introduce you to this pattern, and so the next page that's in our quote normal packet, the normal materials, you have a little bit of that same idea, where you have a warm-up, and it gives us a little summary here. If we wrote these out the long way, which is kind of what we did on the first side of that worksheet, we did the first few, we wrote them out the long way, and then we found that the middle two would add up to 0, would cancel out, however you would ever say that. Our simplified form would only have 2 terms. These two, again, we see that actually this one, my minus would be next, but they would again cancel out. Remember, 1 times 1 is 1. So 1 is a perfect square. And then I think we can start to see that the pattern is the middle part will cancel out. So by the time you get here, perhaps you don't even write the negative 6ab and positive 6ab, because you just know they are going to cancel out anyway and leave us with 4a squared minus 9b squared. We really want to get to the point that we don't need to distribute all that. We want to just be able to go to that right-hand side because we recognize that it meets this pattern. It's important because when we go backwards, we need to recognize that pattern. So those resulting answers are called the difference of squares, as I talked about on the other page. If I'm trying to factor a difference of square, first make sure that it is actually a difference of squares. It has to be subtraction. If it's a plus, it's probably prime. And you have to be able to take the square root of both terms and get nice rational numbers. No decimals, no fractions, all right? And then the rule is a squared minus b squared gives us the square root of a squared, which is a, plus b times a minus b. So that they look the same, but one is positive, one is negative. And you can always check your work by distributing. So that should sound familiar about checking work by distributing, because that's how we can check all of our factoring. So the next pages are going to be very similar. This is very similar to what we just did on the other page. So I'm just going to go through and fill in a few of these. Okay, I'm back. If you hadn't worked those in advance, you can pause things now and try to work them. Be sure that you would get the same answer. I see I left off a parenthesis up there. Sorry about that. Notice that my factors in each set of parentheses look the same except the sign. And that number 5 is prime. It is not a difference of squares because it is not a difference at all. This is a plus, so it is not a difference. So I cannot factor it as k minus 5k plus 5. I can also not do just 2k plus 5s, because if you sometimes people think, oh, well, it's just this. But if you had this and you distribute it, you would end up with 5k and another 5k, and then they don't cancel out, and there would be 10k, that double combo in the middle. There is no middle term. It's just k squared plus 25. So that cannot be factored, number 5 there. So this is not equal to this. Not the same. All right, so that is why this cannot be the factorization of number 5. All right, so I'm going to skip ahead to show you some like the very bottom of your homework page. I was going to skip ahead a little sooner, but I figured I should show you again a couple of these that have multiple variables, in case that might throw anybody off. I like to just go ahead and set up my 2 sets of parentheses to get 4h squared, 2h, 2h, to get 25g squared, 5g, 5g. Notice g squared was at the end, so both of the last terms get g's. It's not gh squared, like not g squared, h squared together. All right. And then down here on number 13, this one is together, x squared, y squared together. So the first term needs both an x and a y. The x and the y are going to be part of the same term. And then for the 1, plus 1 and minus 1. So this is where I get this. And here is this part. And again, 1 plus 1 minus. If we have higher exponents than second power, as long as they are an even exponent, they are a perfect square. because we can take the square root by just dividing the exponent by 2. So this 81, square root of 81 is 9, and then the square root of n to the 4th would be n squared, and 9n squared. And then I'm going to go, so that was from the 81n to the 4th. Now I'm going to go to the 25, plus 5, and minus 5. Right, so there will be times it could potentially factor again, but it would still, both terms would have to be squared, not just the 9n squared. The 5 would have to still be a perfect square, and it's not. So we can't go any further with that. So down here where it says examples with a GCF, let me do a couple here. If you try to go straight to the 2 sets of parentheses, not going to work. You're not going to be able to make them look exactly the same except the sign, because 2 and 72, neither one are perfect squares. So GCF first, they have a 2 in common, leaving us with n squared minus 36. That 2 is going to be part of your final answer. I usually just drop it down right away so I don't forget about it. Now, this part is breaking up using the difference of squares pattern. So n plus 6, n minus 6. Notice that 2 that's on the outside does need to be rewritten with your final answer, but it is only out there one time. It does not go in front of both parentheses. 2 is a very common one, but it doesn't have to be a 2. It could be a larger number, such as a 6. So 6 on the outside, 4a squared minus 9b squared. Common factor could be you have to take out a b. And remember, still any GCF like 4. So inside the parentheses, they should not still have anything in common. So if I would have done 10 and 6, they would still be even, and they would have things in common. So take out your GCF first, even if they happen to already be perfect squares. That gives you what you need to know to do the next page.